Hi class. Today we're going to do part 2 of section 4.2. Section 4.2, but before we go on, let's do a recap. We start at page 24 here. And the goal for 4.2 is to define the 3 common types of reactions: precipitation, acid-base, and oxidation reduction. This talk is going to primarily be about oxidation reduction. And so there are some tables that are important. The first type of reaction is a precipitation reaction, and for that you need to know what is soluble and insoluble. And then you also need to know something about acids and bases, and so there's a slight introduction to that. So let's do that recap real quick. For precipitation reactions, there are the solubility rules. The solubility rules are in 2 parts: the things that are usually soluble and the things that are usually insoluble. And the usually soluble groups are the group 1 metals, the alkali metals, sodium, potassium, lithium, and the ammonium ion. And in fact, those are always soluble, very soluble. Also, acetate, bicarbonate, nitrate, and chlorate anions. Any compound that contains those as an anion is always soluble by this rule. The halides are usually soluble with these exceptions, and the sulfate ion is usually soluble with the exception of the same things that halides precipitate with, but also barium, calcium, and strontium. The odd one out in group 2 here is magnesium. Magnesium behaves very differently than calcium, strontium, and barium. And then what's usually insoluble are the carbonates, chromates, and phosphates in one group, and the hydroxide and sulfide in another group. The exceptions, the first exception is the metal cations. When these are the anions and these are the cations, it's soluble. But the second group, hydroxides and sulfides, not only have the group 1 metals, the alkali metals, but also the alkaline earths, with the exception of magnesium. So we really need to know what's in this column, and it'd be really good to know what's in this column also. But really commit this to memory, that sodiums and potassiums and lithiums are always soluble, and hydroxides and carbonates are, if it's not of group 1 metals, are normally insoluble. With calcium hydroxide and barium hydroxide happen to be soluble. Anyway, the next thing here are the common strong acids: hydrobromic acid, hydrochloric acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. The only 2 of which that you would encounter in the hardware store are hydrochloric acid, called muriatic acid, and sulfuric acid, which is sometimes used to clean drains and comes in a plastic bottle with a secondary containment of polyethylene bag. So those are the main things we need to know. The acid-base reactions. Acids, of course, produce hydrogen ions in solution. Now, something that hydrogen ions usually associate with water and form what's called the hydronium ion, but we basically treat them as equal. So H3O plus and H plus may be written equivalently. H plus aqueous is in fact, in reality, H3O plus. And a base is a substance dissolved in water will yield hydroxide ions. Now, among acid-base reactions can involve the transfer of a proton. Let's see. Acid-base reactions can involve the transfer of a proton, but that is, a hydrogen ion from one species to another. But the more common expression of an acid-base reaction is the formation of what we call neutralization, in which that transfer of a hydrogen ion from, say, HCl to the OH minus here yields water. And that's a subset of acid-base reactions, the formation of water. It's called neutralization. And in all of this, the net ionic equations are important. For neutralization reactions, the net ionic equation is always either H plus OH minus yields H2O, or H3O plus OH minus yields 2H2O. Okay, so this is where we left off. Oxidation reduction reactions. I believe earlier in the year we talked about calculating the charge on transition metals based on the compounds that they form. This is going to be very much like that. We're going to be talking here about the change in oxidation number. Now, oxidation number is a concept very similar to charge, and sometimes it is exactly the charge on the ion. But in a compound, it may not be the charge on the ion. So in this case, sodium as an element, all elements are said to have an oxidation number of 0. And in this case, in a compound, it has a charge of +1. In this case, on sodium, the charge is the same as the oxidation number. And this underwent a change in oxidation number. This went from sodium 0 to sodium 1, while chlorine, as an element, it has an oxidation number of 0, goes to its ion, Cl-, it has an oxidation number of -1. So this oxidation number went up from 0 to 1, and this oxidation number went down from 0 to -1. And that's what happens in redox reactions. One of them becomes reduced and the other oxidized. At this point, it's important to talk about what is oxidation and what is reduction. And an acronym for knowing this is Leo. Think of a lion going grrr. This says loss of electrons is oxidation, and gain of electrons is reduction. And so right here, this has the charge or oxidation number increasing, and this has the charge or oxidation number going decreasing. That is, going more negative. Negative. Okay? So, that is important to know. Oxidation reduction reactions. The sodium loses electrons, the chlorine gains electrons. For redox reactions of this sort, oxidation equals loss of electrons, reduction is gain of electrons. Sodium is oxidized, chlorine is reduced. Sodium functions as a reducing agent because it provides electrons or reduces chlorine. Chlorine functions as an oxidizing agent, oxidant, because it effectively removes electrons from, or it oxidizes sodium. As I like to say, the reason why we use antioxidants is because oxidants do happen. Okay, some redox processes do not involve the transfer of electrons. And that's why we talk about oxidation number. So it's either the explicit charge or it's otherwise calculated. So in this case, hydrogen plus chlorine, of course these have oxidation numbers of 0, go to HCl. And in this case, we treat chlorine as though it formed an ion and hydrogen as though it formed an ion, and say that this oxidation number is -1 and this oxidation number is +1. The product of this reaction is a covalent compound, so transfer of electrons in the explicit sense is not involved. The oxidation number or oxidation state of an element in a compound is the charge its atoms would possess if the compound was ionic. You got it? Let's say it again. It's the oxidation number of an element in a compound is the charge its atoms would possess if the compound was ionic. Rules for assigning oxidation numbers. The oxidation number of an atom in an elemental substance is 0. The oxidation number of a monoatomic ion is equal to the ion's charge. The oxidation numbers for common nonmetals, like carbon or boron, are usually assigned as follows. Hydrogen is +1 when combined with nonmetals, like carbon and oxygen, and -1 when it's combined with metals. These are compounds with the names of hydrides, like lithium aluminum hydride and sodium hydride. But this is the more common situation that we're going to be encountering, is we're going to be considering hydrogens as having a +1 oxidation number when it's in a compound. Oxygen is -2 in most compounds, But if it exists as a peroxide, it's going to be -1. And although we're not going to encounter it, there's what's an ion called a superoxide, which would have an oxidation number of 0.5. And their oxygen can have positive values, not only when it's combined with F. There's what's called an oxonium ion, but we're not going to be involved in that in this class. For your purposes, consider oxygen to have an oxidation number of -2. Halogens. Halogens have an oxidation number of -1. So this is the rule. Hydrogens have +1, oxygen has -2, and halogens have -1, just like they would in most ionic compounds. The sum of the oxidation numbers for all atoms in a molecule or polyatomic ion equals the charge on the molecule or ion. Okay, so you follow the guidelines in this section to assign oxidation numbers to all the elements in the following species. A, H2S. According to the guidelines, the oxidation number of H is +1. Using this oxidation number and the compound's formula, the guideline 4 may be used to calculate the oxidation number for sulfur. So the charge is 0, which is equal to 2 times, that is, the 2 hydrogens, 2 times a +1, plus 1 for the 1 sulfur times X. What is X? Well, you solve that, and the answer is X equals -2. So the oxidation number of sulfur in hydrogen sulfide is -2. So let's look at sulfur in the sulfite ion. So oxygen has an oxidation number of -2, but this ion has a charge of -2. So we're going to say -2 is going to equal 3 times -2, that is, the 3 times the charge on the oxidation number on the oxygen, plus 1 for the 1 sulfur, X. And you solve for X there, and you get that the oxidation state, or oxidation number, of sulfur is +4. Following the guidelines, assign oxidation number to all the elements in the following species. Sodium 2SO4. You know that sodium forms a monoatomic ion, and that will be a +1 ion. And so you know its oxidation number is +1. Each of the 2 sodiums has an oxidation number of +1. Then you have the ion SO4. And in this case, you're going to have -2 is equal to 4 times the oxidation number of oxygen, which is -2. So 4 times -2 plus 1x. So you solve for x and you get x equals +6. So this is sulfur in the +6 oxidation state. Oxidation reduction reactions. Using the oxidation number concept, an all-inclusive definition of a redox reaction has been established. Oxidation reduction reactions are those in which one or more elements involved undergo a change in oxidation number. Well, that's actually a little stilted. Oxidation reduction reactions are those in which 2 or more elements undergo a change in oxidation number. Because if one goes up, another one has to go down. So, hence, there's always oxidation and reduction. So, oxidation is equal to an increase in oxidation number. Reduction is a decrease in oxidation number. In combustion reactions, these are a kind of redox reaction in which the reductant, called a fuel, and the oxidant is often but not necessarily molecular oxygen, react vigorously and produce significant amounts of heat and often light in the form of a flame. Example, rocket fuel. Well, in this case, it's not oxygen that's the oxidant, but ammonium perchlorate, and the reductant is solid aluminum. And so the solid aluminum goes from an oxidation state of 0 here to this oxidation state in here, where it's, let's see, 3 times minus 2 is minus 6, and then you divide that by 2. So aluminum has a plus 3 oxidation state. It also has a plus 3 oxidation state here. And chlorine has gone from a, well, let's see, it's plus, this minus 1, this whole thing is a minus 1. This is 4 times minus 2 is minus 8. So minus 1 is equal to minus 8 plus x. So x is plus 7. This is a plus 7 oxidation state. And the nitrogen goes from a, a minus 3 oxidation state to a 0 oxidation state as an element. Types of redox reactions. Single displacement reactions are redox reactions in which an ion in solution is displaced or replaced via the oxidation of a metallic element. So in this case, copper is oxidized. It goes to copper in the 2+ oxidation state, and silver is reduced in going to the from silver in the +1 oxidation state to silver in the 0 oxidation state. And so this just shows a silver solution with copper wire, and the copper becomes oxidized, becomes the copper in solution, and the silver is deposited on the copper and falls off. So a copper wire is shown next to a solution containing silver. Displacement of dissolved silver ions by copper ions results in accumulation of gray-colored silver metal on the wire and development of a blue color in the solution due to dissolved copper ions. Balancing redox reactions via the half reaction method. Okay, I'm going to read these slides, and balancing redox reactions is a skill, and a skill that I hope we can develop, but we may have to move on to take care of other things. But let's continue. Redox reactions that take place in aqueous media often involve water, hydronium ions, and hydroxide ions as reactants or products. So oftentimes we have to throw these things in the right places. Although these species are not oxidized or reduced, they do participate in the chemical change in other ways. These reactions are difficult to balance by inspection. That's the truth. One very useful approach to balance these types of redox reactions is to use the half reaction method. Steps for balancing redox reactions. Write the two individual half reactions, the oxidation and reduction. Balance all the elements except for hydrogen and oxygen. Oxygen and hydrogen. Balance the oxygen atoms by adding O2 molecules on the other side. Balance the hydrogen atoms by adding hydrogen ions on the other side. Balance charge by adding electrons. If necessary, multiply each half reaction's coefficients by the smallest possible integers to yield the equal number of electrons in each. Add the balanced half reactions together and simplify by removing the species that appear on both sides of the equation. For reactions occurring in basic media, excess hydroxide ions, carry out these additional steps. Add 8 OH minus ions to both sides of the equation in numbers equal to the number of H plus ions. On the side of the equation containing both H plus and OH minus ions, combine these ions to yield water molecules. Simplify the equations by removing any redundant water molecules. Finally, check to see that the number of atoms and total charge are balanced. So, for example, we have dichromate plus iron 2 yields chromium 3 and iron 3. And so you split this into two half reactions. Iron 2 going to iron 3, and chromium in this compound going to chromium 3. It would help to know what the oxidation state of chromium here is. It's 7 times minus 2 is minus 14, and minus 2 is equal to minus 14 plus 2 times the oxidation state on the chromium. And so your minus 14 will move to the other side of the equation, giving you plus 12, and then you divide it by 2, it's 6. So this is chromium in the 6 plus oxidation state going to chromium in the 3 plus oxidation state. Okay, balance all elements except oxygen and hydrogen. The iron half reaction is already balanced, but the chromium half reaction shows 2 chromium atoms on the left and 1 chromium atom on the right. Changing the coefficient on the right side of the equation to 2 achieves balance with regard to chromium atoms. Balance the oxygen atoms by adding H2O molecules. The iron half reaction does not contain oxygen atoms. The chromium half reaction shows 7 oxygen atoms on the left and none on the right. So 7 water molecules are added to the right. Balance hydrogen by adding H plus ions. The iron half reaction does not contain H atoms. The chromium half reaction shows 14 atoms on the right side and none on the left. So 14 H plus ions are added to the left. Right there. Balance charge by adding electrons. The iron half reaction shows a total charge of 2 plus on the left side, the iron 2 ion, and 3 plus on the right side. Adding 1 electron to the right side brings that side's total charge to 3 plus 1 minus is 2 plus, and the charge balance is achieved. The chromium half reaction shows a total charge of 12 plus on the left side, and on the right side it's 6 plus. Adding 6 electrons to the left side will bring that side's total charge to 12 plus minus 6, or 6 plus, and charge balance is achieved. Multiply the 2 half reactions so the number of electrons in one reaction equals the number of electrons in the other reaction. To be consistent with mass conservation, and the idea that redox reactions involve the transfer, not creation or destruction of electrons, the iron half reactions coefficients must be multiplied by 6. So you see, at this point, what we're going to do, we're going to cancel these 6 electrons on this side with these 6 electrons on this side, and then add everything together, add all the products together and all the reactants together to get the balanced equation. Add the balanced half reactions and cancel species that appear on both sides of the reaction. So it's going to be the 6 electrons here and the 6 electrons here, and that's it. Only the 6 electrons are redundant species. Removing them from each side of the equation yields the simplified balanced equation here. A final check of atom and charge balance confirms the reaction equation is balanced. Iron 6, 6, chromium 2, 2, oxygen 7, 7, hydrogen 14, 14, and the charge on each side is 24 plus. And that is the end of that. Have a good day.